So good evening, everyone. Let us continue our discussion and try to understand further the concept of life cycle analysis. So in this week, which is the fifth week lecture, so we'll basically try to understand how to use the processes, databases, etc., and how to use them for performing the various stages of life cycle, that is the life cycle inventory, the life cycle impact assessment, and the life cycle interpretation. Okay, so the main three stages, and how to correlate the findings with the goal and scope, and how to perform how the various databases and softwares work. So we'll try to understand that, and we'll try to understand the concept in more detail. Okay, so in a lot more detail as compared to the previous classes. So that is the main idea of this week, of the fifth week lectures. So let us revise it. Let us start. So 21st lecture, it is on unit process data and LCI databases. So, as we studied last class also, what is unit process? So, it is a subdivision of the product system assuring a unique or a group of activity operations. And here, there are basically two types of flows. Okay, so one is intermediary flow, that is happening between one process to the other. That is, for example, in this case, it is linking UP1, that is unit process 1, with UP2, unit process 2. That is basically called the intermediary flow, and that is basically related to economy. Okay, so it is also known as economic flow. So it links two unit processes, one or more represents the function of the unit process. So it shows the characteristics of the both the coming and going uh, unit processes. Okay, and that is basically the intermediary flow. Whereas the one which is mainly required for our purpose is the elementary flow. Okay, so elementary flow is basically linking the unit process with some with the environment. Okay, so it is coming and going to the environment. Okay, so this is elementary flow which is coming from the environment to the unit process one, and this is the elementary flow which is outgoing, that is the output. Okay, so it is going from UP1 to environment. So basically we can call this to be an environmental intervention for the unit process with respect to the unit process. So now if you remember this slide, basically, so in theory we can say that all processes required to fulfill the function should be included. Okay, so basically we may mostly have five processes. Okay, mainly we have five processes for any type of product. Okay, one is resource acquisition, or acquiring raw materials. One is manufacturing, that is production. One is distribution, that is transportation. One is use, that is the basically for what the product was made. Okay, so utilization, and last is end of life, that is disposal. So basically there are five parts or processes in the whole life cycle of a product. Okay, and for that we have inputs, that is the elementary flows in terms of natural resource extractions, which I told you, raw material, and also various forms of energy such as solar energy, land use. Okay, and the elementary output flow is basically in terms of emissions and other environmental interventions. So emission can be in air, water, as well as soil, three ways. So in air it will be carbon dioxide, sulfur dioxide, particulate matter, volatile organic compounds. In water it can be PO4, NO3, phosphate, nitrate, that results in basically eutrophication. And soil it can be in the form of pesticides, okay, metals, etc., and also some form of disposal, okay, waste, okay, waste, disposing of waste. And also other than that there can be other environmental interventions such as radiation, heat, noise. Okay, so these are types of some sorts of pollution. Okay, and all this have been done to basically obtain a product. Okay, so product is basically the function which we wanted to achieve. Okay, so everything has been done for this purpose. Okay, so that is basically in theory. Okay, but if we like this is an ideal case. Okay, so if we completely do everything, that is a very ideal case. But in reality, okay, so in reality, if like the question comes is like, do we actually need to do everything? Okay, so is complete life cycle required? Okay, is it efficient, is it economic? Okay, so the answer is no. Okay, so uh, the life cycle analysis or the comparison in terms of life cycle assessment, so that has to be based on what is the goal and scope. Okay, so for example, say for example, LCA is comparing different manufacturing processes for the same type of product. Okay, So if we want to compare different types of manufacturing process for the same type of product, so therefore we can definitely say that the product, as it is unchanged, it is the same product, the use and end of life stages are the same. Okay, so it will be because they are the same product. Okay, therefore its utility and end of life stage will be the same, hence we can exclude those. Okay, it is unnecessary. Okay, this is uh, it is like not required. Okay, so it is wasting our time and effort. Okay, so therefore it can be cancelled out. Okay, so what is required is the first three. Okay, so this is basically, if we take everything. Okay, so that is basically called cradle to grave. Okay, cradle is the birth, grave is the end. Okay, but in this case, okay, when we don't need the use and end of life, we are mainly concerned from starting to middle. Okay, so then it is called as cradle to gate study. Okay, so cradle is always the start. Okay, grave is always the end, and in between where we want the gate. Okay, where we want to stop or start, that is called the gate. Okay, so in this case, because we want from start to middle, so it is cradle to gate study. Okay, similarly, if we want to perform a LCA on municipal waste management. Okay, if we want to perform a LCA on municipal waste management, sorry, the stages before the end of life are the same. Okay, because we will assume that everything happening is same, because the product uh, the product is, say for example, we are comparing to similar product and we are concerned about the municipal waste management. Okay, so sorry, if we are comparing two types of products. Okay, so till utilization, because our focus is on municipal waste management, so we are not concerned about all the four processes. Okay, main processes before that we are not concerned, because our LCA is on municipal waste management. So for municipal waste management, what is the process? That is basically the end of life. Okay, so the stages before the end of life are the same, so we consider it to be the same, because we are not concerned about what is happening before municipal waste management, because our target is LCA on municipal waste management. So therefore we can exclude those. Okay, and in this case we will say it to be gate to grave study, because from the middle we are starting, that is gate, and end is basically grave. Okay, so gate to grave study in this case. Now, let us say, take some examples. So, say for example, we want to define the system boundaries. Okay, so let us take a practical example, true example. So, there was a study done in early 90s, okay, which compared a McDonald's and a conventional mom and pop restaurant in USA. Okay, so there was a study done basically in early 90s, that is 1990s, which compared a McDonald's and a conventional mom and pop restaurant. So, after investigating, okay, after finding the boundaries, basically, so they found these results. Okay, so they found that the boundaries, like for comparing, the boundaries must be equivalent. Okay, so taking same parameters, okay, of same functional units, they tried to compare. Okay, so if you see here, McDonald's basically, so that was on agri-food production. Okay, so that was based on agri-food production, and conventional mom and pop restaurant also, so they also, it was for there also it was same. In McDonald's, there was a process called transportation. Okay, so it was also same for conventional mom and pop restaurant. There in McDonald's, there was centralized preparation. Okay, but here it was, maybe it was not centralized, but they have not given the data. Okay, they did not found it. They were not clear. Okay, so so it was blank. Then they checked about the packaging. Okay, so in McDonald's it was disposable packaging. However, in conventional restaurant, is it was basically, there was no concept of packaging. Okay, because the customers used to come, they used to eat in dishes. Okay, so they therefore had to clean. Okay, so there was, because the dishes had to be cleaned for reuse, so it was cleaning reusable dishes. In McDonald's, there was food cooking. Okay, so that is obvious. So that was same in conventional restaurant, food preparation and cooking. So because maybe yeah, in McDonald's the preparation part was not there, because maybe the food, like the ingredients, okay, raw materials, okay, basically the vegetables and everything, so it came from other places. Okay, so they just had to cook. However, in conventional restaurant, it may have been like the preparation, that is like cultivation of crops and everything had also occurred, besides the restaurant. So it was food preparation as well as cooking. Okay, and then cleaning, heating and lighting, so it was same in conventional restaurant. And food, and lastly based on end of life. Okay, so it was, there was both food as well as packing waste management. Okay, packaging waste management, but here There was no concept of packaging in conventional restaurants, so it was only food waste management. Okay? So like this, the boundaries were found out, and they were found. It should always be equivalent. Okay, so that was because physically, if we say what will you mean by boundaries? So in terms of restaurant, it will be the walls basically, right? So physically, the boundaries meaning is the walls of the restaurant. In this case, in LCA, it meant that the boundaries must have same reality, covers same reality. So the same function or service should be provided. Okay, so boundaries must cover same reality, which meant same function or service provided. So when you compare the same function, so the results were like this between McDonald's and mom and pop restaurant. Okay, so from that example, okay, we can say that there are basically three rules to define the boundaries. Okay, so there are basically three rules to define the boundaries. One is the compared systems must provide the same function. Secondly, the included processes are those which contribute more than a fixed percentage cutoff criteria of A, the total mass of the inputs to the system, B, the total energy demand of the system, and C, the total emissions of an environmentally relevant substance. Okay, so it should contribute more than a fixed percentage of either of total mass of input or total energy demand of system, or thirdly, total emissions of an environmentally relevant substance. And the third rule is the identical stages or processes between compared systems can be excluded only if this does not affect their functional equivalence. Okay, so these are basically the three rules to define the boundaries, and the first and third rules basically apply to comparative studies because it is on comparison. The compared systems must provide the same function, so it is comparison. And three, the identical stages or processes between compared systems. Okay, so that can be excluded only if this does not affect their functional equivalence. So these 1 and 3 is on comparative studies. Okay, the rules 1 and 3. So continuing in the 22nd lecture. So now let us see about exclusion of identical processes. That is basically the third point which was mentioned. So here, if you see here, so comparative LCA, say for example, we have done comparative LCA on two herbicides. Okay, so herbicides, as we know, it is basically it is chemical which is used to control undesired plants, which is also known as weeds. Okay, so these are basically undesired plants which need to be removed in the cultivating land. Okay, so in this case, if we consider a functional unit as producing 1 kg of wet. Okay, so let us consider the functional unit to be producing 1 kg of wet. So in the first case, if you see, for producing 1 kg of wet, we have like there has been use of pesticides. Okay, so pesticides production is there, as well as herbicide A production has been there. So after that, the process follows, and there is application of pesticides as well as application of herbicide A plus the tillage, that is basically the preparation of land for growing crops. Okay, so yeah, because of the utilization of all the three unit processes, basically it resulted in harvesting, that is collection of crops. Okay, and that resulted in 1 kg of production of 1 kg of wet. Okay, so that is the first case. And second case also similarly, let us say that instead of herbicide A, we have used herbicide B. Okay, so there also the first process basically it meant production of pesticide and production of herbicide B, that resulted in the that gave rise to the function of application of pesticide and application of herbicide B, along with tillage, that is land preparation for crops. And because of this, all the functions of these three unit processes, we got harvesting. Okay, of 1 kg of wet. Okay, so both produce 1 kg of wet. Okay, now let us say that if yield differs with each herbicide. Okay, okay, let us assume that the herbicide A and B had different potential. Okay, say for example herbicide A. Okay, in case of herbicide A, we found, like, that is in this case, first case, we found that 4000 kg of weight was produced per hectare. Okay, whereas in case of herbicide B, it was found that 5000 kg of weight was produced per hectare. Okay, so that meant that the production of 1 kg of wet with herbicide A, it needed 25% more land. Okay, because the production per hectare was less. Okay, less kg of wet was produced in herbicide A. That means to have an equivalent production of the equivalent production of wet basically as compared to herbicide B. Herbicide A basically needed to be used 25% more. Okay, more land. So basically, 25% more land had to be used for producing the same. Okay, so say for example, for producing 5,000 kg of wet, or producing 1 kg of wet, 25% more land had to be used when herbicide A was used. Okay, so that meant that 25% more pesticide needed to be used. Okay, and 25% tillage extra required, and 25% more harvesting or crop collection was required. Okay, so sorry, so all processes had to be so therefore all processes must be included to find out what is actually happening. Okay, so then only we'll get a fair idea of the results of the life cycle analysis. That's why all the data is every, like, the inventory is very much important. Okay? So that's what it is said here. So data requirements is essential. Why? It is to be able to evaluate the validity of the results and to fulfill the goal of the study. Okay, so data quality requirements should therefore be specified, and this should take into account quantitative and qualitative aspects of the data and of the collection methods. Okay, so there like various parameters are there. They should take into account quantitative and qualitative aspects of the data and of the collection methods, such as data quality, data source, data type, that is it measured, calculated, or estimated, data nature. Okay, is it point estimate or stochastic, that is which involves a random variable, or and also the data aggregation level. Okay, so is it connected or separated, disaggregated. So all these factors keep in mind, and it also results into the quantitative, and it directly plays a role in the quantitative and qualitative aspects of the data. So if we talk about the data source basically, so data source basically can be of two types. One is primary data and one is secondary data. So primary data basically, in case of LCA, it specifically is collected to do the LCA, and which directly is concerned for studying the project. Okay, it directly concerned the studied project at the level of the manufacturer. Okay, at the manufacturer inputs and outputs of a required process, or on the use profile of the product. Okay, or on key parameters. So the data can be based on various aspects. Okay, it can be at the manufacturer inputs and outputs of a required process, it can be on the use profile of the product, or it can be on key parameters. Okay, but it is specifically collected to do the LCA, and which directly concern the studied product. Okay, so that is basically the primary data. And secondary data, it is not specifically collected to do the LCA. So primary is for LCA, secondary is not for LCA data. Okay, so this data can be from literature on a process, example theoretic or empiric model, a standard design criteria. Okay, or average data on inputs and outputs of a unit process found in LCI databases. Okay, so these are some generic data, it is not specific data. So like always primary data is always specific data which we need for the LCA, and secondary data is some generic data which is not directly required for LCA. Okay, it is for more knowledge purpose. Okay, so taking from literature or some databases, it gives a certain average idea, but which is not specific to the LCA which we are concerned to perform. Okay, so now if we say LCI, that is life cycle inventory in short, the product system has been defined and is made up of all the linked unit processes fulfilling the studied function. Okay, so these are some of the processes or unit processes. Okay, and they basically fulfill some they basically fulfill the studied function. Okay, which is this. Okay, and they're connected basically, they are explicitly connected to one another. So it can be connected as well as disconnected also. So if it is connected, it's called aggregated. If it is disconnected, it is disaggregated. And function is the basically the goal we want to achieve. Okay, the product, something we want to achieve basically. Okay, so that is the outcome. Okay, of that, for doing the performing these processes. Okay, so that is the function what we want to achieve. So if you see the unit process, okay, or a process basically in short, for each process the inputs and outputs are quantified. Okay, in LCI inventory, the inputs and outputs are quantified. So if you see here, elementary flows are happening. So which is coming is in elementary flows in, and which is going from the process, it is elementary flows out. Okay, and apart from that, there is inputs from technosphere. Okay, so technical inputs are there, and also products. Okay, output is the products, that is basically the outcome of that process, and that is transferred to other processes or function of the system. Okay, so that happens for each process or unit process. Okay, so Basically, life cycle inventory, it relates all inputs and outputs of all processes to the functional unit and aggregates them. Okay, life cycle inventory, it basically relates all inputs and outputs of all processes to the functional unit and aggregates them. So here if you see, it is inventory of elementary flows out outputs, and here it is inventory of elementary flows in inputs. So this is the, say, function. Let us consider that function as the functional unit. Okay, so this will be obtained by adding or aggregating all the elementary flow of inputs and outputs going in and out of the unit processes respectively. Okay, so that is how the life cycle inventory is calculated. It relates all inputs and outputs of all processes to the functional unit and aggregating them. Okay, that is how we get the value. Okay, life cycle inventory value. So if you see the basically if you see the algorithm, okay, the algorithm of LCI procedure. So the algorithm is such. Okay, so first there is goal and scope definition, then there is preparation for data collection, then there is data collection, then there is validation of data, then relating data to unit process, then relating data to functional unit, then data aggregation, then refining system boundaries, and finally the inventory is completed. Okay, but before completion is reached, okay, so in the stage of refining, like the pre-final stage, that is refining system boundaries, we have to see that additional data or unit processes are required or not. Okay, and if it is required, okay, so we have to go back to preparation for data collection, and there we have to revise the data collection sheet. Some say for example we needed some extra data or unit processes which we did not initially had written there in the data collection sheet. Okay, so we have to revise that data collection sheet, okay, so that we can include all the additional data unit and unit processes which are required. Okay, and this relate, and also the relating data to functional unit and the data aggregation. So these two stages are basically taken care by the LCA softwares. Okay, so the relating data to functional unit and data aggregation, they are generally done by the LCA software. Okay, so the LCA databases basically. So what is like what is followed there. Okay, so like why it is important basically. So the practically it is impossible to quantify all the flows of all processes. Okay, it is practically impossible because there will be infinite number of flows. Okay, so we only basically consider the main ones. Okay, so there was like in last classes there was I forgot the parameter, like only I think which have point more than 0.5% threat. Okay, so all of those flows are considered. Less than 0.5% are removed. Okay, I exactly forgot the value, but there is some threshold value. Okay, so that is why it is practically impossible to quantify all the flows of all processes. The length of supply chains is in theory infinite. Each economic activity is linked to almost all the other. So even if only limited to the most important processes are taken, redoing the data collection all over again for key sectors such as base materials, energy production for each LCA would be incredibly inefficient because it is not possible theoretically practically to even perform the data collection for only the key sectors. That is also, it is not efficient, it is not practically realistic. Okay, so there comes the use of LCI databases. Okay, so as it is not possible for performing the data collection for each LCA, okay, even for the key sectors, there we use the LCI databases. So, as I told you, there are various types of databases. One is disaggregated and one is connected process databases. Okay. So, there are two types of databases. One is connected and one is disaggregated. The data available for each unit process. Okay. So, it is present. The links between processes are explicit. That is clear, as you can see here. And the inventory must be recalculated every time. Okay. So, because as you saw here, so if something is missing, okay, you need some extra information data you need process, you have to again refine and revise it. Okay, so therefore the inventory must be recalculated every time. And some of the examples of databases are EcoInvent version, UCLCI, the US lifecycle inventory, which is a relatively new version. Okay, so like new version has come. So these are some examples of databases. Okay. So the types of databases, so disaggregated and disconnected process databases are there as we studied. So data available for each unit process is present. The links between processes have to be made by the user. Okay, and example, UCL USLCI, okay, old version, research centers internal databases. So basically these are examples of the disaggregated. So uh, so as you saw here, databases are of two types. One is disaggregated and one is connected. Okay. So in case of disaggregated, the data available for each unit process. Okay, and the links between processes have to be made by the user. And some of the examples of disaggregated databases are US LCI, which was the old version, research centers, internal databases, etc. Okay, so this is yeah, I think this is the connected the process database, and this is the example of disaggregated or disconnected process database. Okay, so the US LCA new version has the connected process database, also the eco-invent version, whereas the US LCA old version and research centers internal databases have the disconnected process database. Okay, so that is the this one. And also if you go into detail, so that was if you go more into the connected database, that is the aggregated process database. So here the data is available at the product system level only. Okay, so we'll not get idea of the in the unit processes. Okay, so these are basically black boxes which represent the cradle to gate. Okay, inventory. And some of the examples of process databases are gabi, that is a life cycle assessment database owned by Spera, which is German. Okay, it is a German software. And one is ELCD, which is European Reference Life Cycle Database in majority, and also EcoInvent. So EcoInvent basically, as I told you earlier also, so they have basically the connected process database. Okay, in majority, sorry, mainly basically. And this is the example of the connected process database. Okay, so aggregated or connected. So these are some of the benefits and problems of uh, benefits and problems of aggregated as well as disaggregated databases. Okay, so the aggregated or connected databases, so they have only one use, one benefit, which is user friendliness. Okay, because calculations already done per systems, so that is benefit. Other than that, every other thing is a drawback basically. Okay, so possibility to adapt data sets, it is not possible, because no adaptation possible, because they have a black box model which is cradle to gate. Okay, second is the validity. Okay, validity is issue because they cannot be checked. Okay, and it also depends on database. Contribution analysis also a drawback because they have a low resolution at material level. Okay, although it is possible, but they have a very low resolution at material level. And is it possible to create distributed data sets? No, because they are aggregated. Okay, they are basically connected. So however, it is the opposite in the case of disaggregated or disconnected. So here only drawback is the user friendliness, because they need software for calculations. Okay, so it can be done by manually, or it needs to be done for every process, which is very difficult for performing manually, because there are lots of elementary flows happening, like a infinite number of flows happening. So that is the issue. Apart from that, everything is a benefit. Okay, such as possibility to adapt datasets. So it is possible to adapt individual datasets. Validity depends on database, but it can be checked. Contribution analysis, yes, with high resolution and process level in process level. And is it possible to create distributed datasets? Yes. So all of them are positive, apart from the user friendliness. So these are some of the examples of available process databases. So the various agencies, which are government and research center agencies, which are basically providing the process databases, are one is the EcoInvent, which is a famous one. It's from Switzerland. One is IVAM LCA data, that is from Netherlands. One is Spine at the rate CPM Sweden, IDMAT Netherlands, ELCD Europe, USLCA United States. Okay, so these are some of the government agencies which are providing the databases. And there are also some industrial associations such as Plastics Europe, FEFCO Europe. Okay, so these are also some industrial associations which are providing the databases. And using these databases, there have been many software developers. Okay, so which have created softwares. Okay, so one is the IKP or PE Europe, Germany. So they have developed the software of Gabi. Okay, so one company is Pre Consultants, okay, from Netherlands. They have developed the famous Simapro and EcoIT. One is IFEU Germany, from Germany. So they have developed Umberto. One is Ecobilan from France. They have developed Team, and also there is a company from Athena Institute, Canada. So I don't know what's the name. It's not provided, but they have also divided. They have also developed a software for the life cycle assessment. Okay, so out of them, if you see here, the ELCD Europe database, so that is basically free. Okay, same is the case with US LCI United States, it is also free. And also the industrial association databases such as Plastics Europe and FAFCO Europe. Okay, so those are the free databases. Apart from that, all others have to be purchased. Okay, the rest have to be purchased, be it softwares or the databases. So now let us go into inventory data and LCIA in more detail. So this is an example of inventory data example. So it basically says the CO2 released, okay, per unit. Okay, so if you see here, uh, there is energy, okay, in 1 kilowatt hour electricity. So it is giving the amount of CO2, okay, in as fossil that has been released in terms of kg. Okay, so in Quebec, which is a city in Canada, 1 kilowatt hour electricity produces 0.023 kg, whereas in China it is 0.96 kg, in USA it is 0.71 kg. And like this, there is values given for transport, okay, as well as material, end of life. Okay, so all the values have been provided. This is an example of inventory data. So it has been taken from EcoInvent database, okay, 2.01. So if you use this and find use this for the performing the CO2 inventory, for use this for developing the CO2 inventory for the incandescent light bulb. Okay, so in that for the incandescent light bulb, the cycle stages, basically the main processes. Okay, so they are manufacturing and packaging, distribution, use, waste collection, and end of life. Okay, for the incandescent light bulb. So in manufacturing and packaging, sorry, so one is glass. The ingredients are glass, copper, cardboard. In distribution, transport, freighter, that is ship or aeroplane which carries a huge amount of goods. Okay, so basically it is a ship. Okay, and it is a transport truck. Okay, uses electricity, waste collection, transport truck, correct, done by transport truck. And end of life, the landfilling of glass, copper, and cardboard. Okay, so here, uh, initially, if we like, these are some of the values of the these are some of the specifications of the materials, okay, and the services. Okay, so initially, if we try to find out the amount per fu, that is a functional unit. So let us consider for the bulb. Okay, so the glass, copper, and cardboard, let us consider that 10 amperes current flow was the functional unit. Okay, so if you multiply 22.8 into 10, you will get 228 gram. Okay, similarly 12 gram and 232 gram. Here we considered that 472 grams CO2 was released in a kilometer. Okay, so if you multiply 472 into 10,000, you will get 4.72 ton kilometer. Okay, similarly 2.36 ton kilometer for transport truck. And use electricity, so just multiply 60 into 10,000, we get 600 kilowatt hour. The transport truck, again 472 into 50, that is 20.6 kg kilometer. And the end of life, so these are some standard values. For glass and copper, it is 240 gram, and cardboard is 232 gram. Okay, that is amount per functional unit. And a CO2 per unit, basically we got it from here. Okay, so from the inventory EcoInvent inventory data example. So if you see here, glass, okay, glass is 0.52 kg per kg. So it is this one, 0.52. Okay, so copper is 3.1. So where is, yeah, this is copper, 3.1. Then cardboard is 1.1. Cardboard 1.1. This is corrugated board packaging. Then transport freighter, it is 0.010. This one. Okay. Then transport truck is 0.12. Okay. Then 0.023, that is for electricity. So yeah, electricity, taking Quebec example, Quebec city example, 0.023. Then kg per kilowatt hour. For waste collection, again 0.12. Okay, same truck. Okay, it is 0.12. And for end of life, it is 0.010 kg per kg for inert waste. Okay, so these are inert waste. And cardboard, it is 0.014. Okay, kg per kg. So this is the CO2 per unit. Okay, so multiplying both this, okay, this and this, we get CO2 per fu, because it is kg CO2 per unit and amount per fu. Okay, so this is kg per unit, unit per fu. So multiplying this, we will get kg per fu. So CO2 in kg per functional unit. Okay, So multiplying both, we get 0.12, 0.037, 0.26, 0.041, 0.25, 14. Okay, so 14 is basically 96%. Like it has been found that 96% is the this one is a release, heat release. Okay, heat release. So 4% is the incandescent light bulb efficiency. Okay, generally it used to be 5% if you remember, so it is 4% in this case. And then 0.0025 is the value of the multiplication for waste collection, and 0.0024, 0.00324 end of life. Okay, so totaling, we will find that total 14.5 kg per functional unit of CO2 is released. 14.5 kg CO2 is released per functional unit in the case of incandescent light bulb. Okay? So that is the example of the inventory data. Okay, so how to use the inventory data and calculate the values. Okay, so now let us go to impact assessment. Okay, so let us now to understand the impact assessment. We have calculated the inventory basically. So this was, we took the example and calculated the values. Now if you see here, the life cycle impact. So this is the basically the standard picture. So standard pictorial representation. So there is elementary flows of inputs and outputs. So they basically result in the assessment of impact categories. Okay, so they basically result in the designation of the impact categories, which is responsible for which directly is impacted by their elementary flow, be it global warming, ozone layer depletion, land use, natural resource depletion, acidification, eutrophication, photochemical ozone generation, human toxicity, co-toxicity, etc. And ultimately, after performing the assessment, okay, we try to find a final score, okay, which is a single score, like in this case, okay, but for this impact categories, okay. So that is what it is, basic idea of impact assessment, okay, life cycle impact assessment. And in this case, and in this case, the environmental mechanism and indicator is such. Okay, so basically if you say that global warming, so that is uh, the first basically we are basically here seeing the environmental mechanism is basically the cause and effect chain. Okay, so basically global warming, the first the if you say the first thing which is happening, okay, first thing which is happening, it is the GHG or greenhouse gas emission, which is because of the elementary flow. Okay, so we can say it to be the zero order effect, or the main it is the main event happening. Okay, so for that, what is the cause and effect chain? Okay, so GHG emission, which is elementary flow, so that is basically resulting in the infrared radiative forcing. Okay, so that is called the first order effect, because it is that is mainly responsible for this to be happening. Okay, so that is a category. Okay, so this is a first order category, that is a category indicator. This is a first order effect. So because of this infrared radiative forcing, what is happening, this is resulting in increase in global temperature. So that is a second order effect. Okay, so it was the primary cause. This resulted in infrared radiative forcing, which was the first order effect. That resulted in the increase in global temperatures, which is the second order effect. And that resulted in the sea level rise due to water expansion and glaciers melting. So that is the third order effect. And like such like we as such like as similarly, following that, if we go to end order effect, we'll find that it will damage the human health as well as the ecosystems. Okay, so likewise, it is the first, second, third, and thereafter, if you go to the end order effect, likewise, it will result in damage to human health and ecosystems. So all taking all those things in mind, okay, so the impact 2002 plus basically approach for impact assessment. Okay, so that was basically mainly formulated by by a team led by Joliet. Okay, Joliet and others. So they have published the results in a research paper in life cycle journal of life cycle assessment in 2002. And because they produced it, that's why it is in 2002 it was developed. So it is known as impact 2002 plus. So basically they had a concept of both midpoints and endpoints, okay, for impact assessment. So based on the midpoints, they selected the damage categories, and based on that they tried to obtain a final score. Okay, so elementary flows, it resulted in the midpoints of various impact categories, and that resulted in endpoints in damage categories, which basically were four. One was human health, one is ecosystem quality, one was climate change, and one was resource use. Okay, so this is one of the examples. So this was the person basically which had given that, which has suggested that impact 2002 plus approach. Okay, so based on that approach, okay, so this was basically it has been taken from that paper, okay, research paper. So again, it was published in 2004 in International Journal of Life Cycle Assessment. So that has also been that has also been considered by the UNEP and SETEC. Okay, so UNEP is the United Nations Environment Program, and SETEC is Society of Environmental Toxicology and Chemistry. Okay, so both these organizations, they've also considered that approach, and they have provided the guidelines for the life cycle initiative framework. Okay, so the LCI results basically based on the results, we have to find the various categories, okay, midpoint categories, which will be considered for that particular data. Okay, is it related to human toxicity, casualties, noise, photochemical oxidant formation, ozone depletion, climate change, acidification, eutrophication, ecotoxicity, land use impacts, species and organism dispersal, abiotic resources depletion, minerals, energy, fresh water, biotic resources depletion, etc. So these are the midpoint categories to be considered for each data, okay, which is affecting them, okay, which can affect that category. And based on this, we have to find a damage category, which is the endpoint. Is it human health? Is it biotic and abiotic natural environment? Is it biotic and abiotic natural resources? Or is it biotic and abiotic man-made environment? Okay, so these are basically this from these categories only they have tried to even further bifurcate. Okay, so these are some of the damages. Okay, so like this they have provided the guidelines for the framework, okay, life cycle framework, and this has been provided by the UNEP and SETEC. So if you see broadly the based on these elementary flows, which are the impact categories that need to be assessed. Okay, so human toxicity, that has to be assessed for pesticides and metals. Respiratory effects that is required for SO2 and PM, sulfur dioxide and particulate matter. Aquatic ecotoxicity is required for your, again, both these pesticides and metals. Aquatic eutrophication, it is required for phosphate nitrate. Okay, global warming is required for carbon dioxide, and non-renewable primary energy, it is for iron ore. Okay, so like this, or even I think it will be also for crude oil. Okay, so like this we have to select those categories based on the flows. Okay, where we have to perform, we need to perform the impact assessment. Based on that, we will be following characterization. Okay, so characterization is basically will be for the case of global warming. Okay, so for the case of global warming, because global warming is directly associated with CO2. Okay, so we have to give a quantitative value, which is an equivalent quantitative equivalent of CO2 for each of the non CO2 cases. Okay, so for example, it means that because in when we are assessing for global warming, the main reason is CO2. So that means we have to, for all the products, okay, we have to find the equivalent value of CO2 that is released for that gas. Okay, or which is the same effect, the equivalent effect of that gas in terms of CO2. Okay, so 1 kg CO2 will be equal to 1 kg CO2, but 1 kg methane, it is equal to say 25 kg CO2 in terms of effect. Okay, on 1 kg N2 it is equivalent to 298 kg CO2 equivalent. Okay, so that is the times of 298 times the effect, okay, of 1 kg in terms of CO2. So that the characterization model, okay, so based on, say for example, for global warming, it was developed by the IPCC. Okay, it is Intergovernmental Panel on Climate Change, and they used to calculate the characterization factors, and it considers the infrared radiative force generated by a greenhouse gas emitted in the atmosphere over different time horizons. That is the first order effect. Okay, cause and chain effect, and that is in the atmosphere over different time horizons, 20, 100 or 500 years. And there are two parameters, okay, basically for this. One is the atmospheric lifetime duration, and the second is heat absorption due to the infrared radiative force. Okay, so these are the two parameters which are the main parameters to consider. So now let us go more detail into life cycle impact assessment. So in practice, for characterization, So there are the three steps. First is the choice of LCIA method. There is a pre-established choice of impact categories, category indicators, characterization model and factors. Second is classification, and third is characterization. So it is the calculation of category indicator results or impact scores. So Sj is equal to summation I CFJI Mi, where Sj is impact category for impact score for category J. Example in kg CO2 equivalent. CFJI is basically the characterization factor of elementary flow I for impact category J. Okay. Example in kg CO2 equivalent by kg of I per kg of I, and Mi is elementary flow related to functional unit, which is example is kg of I. So this is the formula for characterization. Okay, so using characterization factor you can find the impact score for a particular category. So all this after, like, when we see some examples, we will understand it properly. I think in coming classes we will further go deep, so we will understand when we solve the real example problems. Okay, so when we solve the problems, we will understand how everything is performed. Okay, impact assessment and all. So let us first understand it theoretically. So if you see here, for, say for example, this is a small example. So here we need to say, for example, we need to calculate the global warming potential GWP for the incandescent light bulb. Okay, so here the emissions, okay, emissions can be of various types. Even in CO2 only there can be fossil or biogenic, which is produced or brought about by living organisms. So that also is a CO2. One is the fossil CO2, which is the main one. Then there is methane, fossil fuel, sulfur dioxide, dinitrogen monoxide, and your sulfur hexafluoride SF6. So here if you see, so the amount per functional unit kg per fu, so it is 19, 0.60, 0.040, 0.074, 0.0036, and 0.000092. Okay, so that is the amount per functional flow. So amount is the elementary flow happening per functional unit. Okay, kg per functional unit of the given quantity of the given emissions. So the characterization factor that has been found as per the databases. So for CO2 it is 1, obviously. In fossil biogenic it is considered 0. Methane it is 25, SO2 0, N2 298, and SF6 22,800. Okay, so these are the characterization factors. So multiplying both we will get the global warming potential. Okay, so it is 19, 0, 1, 0, 1.1, and 2.1. Okay, so the total is 23.2. So if you see here 19, it is out of 23.2, it is 82%. So the global warming potential total is 23.2. Out of that, 19 is directly coming from CO2. Okay, 82% is coming from CO2, 4% from methane, 5% from N2, and 9% from SF6 in equivalent CO2 terms. Okay, so that is the characterization. After that comes the normalization process. Okay, so normalization basically, it is basically when we convert the functional unit to reference system. Okay? So normalized LCIA profile, it is equal to LCIA profile related to functional unit, that is gets converted to LCIA profile related to reference system, RS. Okay, so this was, if you remember, these were the elementary flows. Okay, so from that we tried to classify. Okay, classification was done, and from that we tried to characterize. Okay, characterization was done. Okay, and that is the equivalent CO2 and equivalent values required, and from there we basically get the normalization. Okay, so that is in the characterization only, like from the per functional unit values we got the per this one reference system values, and that basically gives the ultimate normalization, which is basically reference system equivalent in terms of human health, reference system equivalent in terms of ecosystem quality, reference system equivalent in terms of climate change, and reference system equivalent in terms of resources. Okay, so this reference system can be other product system, example reference product, geographic area for a specific year, which is example Europe in 2008, and geographic area for a specific area per capita, example average European in 2016. Okay, per capita means per person. So example average European in 2016. So these are some of the examples of reference system. So we are converting from functional unit to per reference system. Okay, so these are how we can calculate. So we will, in the coming classes and slides, we will we try to understand how they will be implemented. Okay, so this is basically the finally after that we basically go for weighting and aggregation, and then we finally get the single score. Okay, so based on the elementary flow, we firstly try to classify. Okay, then we try to characterize. Okay, then we went for normalization. Okay, and from that we will weight. Okay, weight in terms of which is important, which is less important. Say for example, this is the most important, this in terms of CO2, the CO2 is the most important and this is the least. Okay, this is megajoule, that is the basically the primary energy. Okay, so that is the least required. So as per that the weighting has to be done, and finally we obtain the single score. Okay, so this is basically the LCIA procedure. The mandatory elements are three. One is selection of impact categories or category indicators and characterization models. Second is assignment of LCI results, okay, inventory results. Basically, it is classification. And third is calculation of category indicator results. Okay, that is basically characterization. Okay, so based on that, the category indicator results are obtained from the LCIA profile, and here there are some optional elements such as normalization, weighting, and aggregation. So this normalization, weighting, okay, so these are not the mandatory. These are not the mandatory ones. Okay, mandatory is up till characterization, classification, and character. So up till here it is the important. Okay, here, up till here it is important. Normalization, weighting, these are not this one, aggregation, weighting, and all these are not. This is basically aggregation, weighting, and normalization. So these three steps are not mandatory in life cycle impact assessment. Okay, so here are some examples of the life cycle impact assessment methods which have been developed over the years, starting from 84, where volumes critics BUS was developed. After that CML, EPS, Eco Indicator 95, EDIP 97, Eco Factors 97, EPS 2000, Eco Indicator 99, CML. So in 2003, a lot of LCI methods have been developed, such as Impact 2002 Plus, which was by Joliet, Tracy, Jepix, Lime, and in 2005 Lucas. For it was EDIP 2003, and finally the last before 2010 it was Recipe. Okay, so that was the most latest version, okay, of the LCI methods which were developed. So these are some of the available LCI methods which have been there: Eco Indicator 99, EDIP 2003, EPS 2000, CML 2001, Impact 2002 Plus, JPIX, Line, Swiss Eco Scarcity, Tracy, Recipe. Okay, so and there is also a link for summary of methods. Okay, so out of that, Impact 2002 Plus and Recipe are one of the comprehensive ones. That's why they have been highlighted in red. So if you can study those, so it will be you can even further learn how the impact assessment has been carried out. But that is beyond the scope of this course, so it has been restricted. So we'll limit our study to our knowledge to here only. So but for more information you can further consult this methods, Impact 2002 Plus and Recipe. They are one of the most comprehensive LCI methods available. So these are the region specific distribution of the LCI methods. So Lucas and Tracy is from US, EDIP, CML, Recipe, the Impact 2002 Plus, Eco Indicator, EPS. So they are mostly from Europe, and Lime is mostly from China. Okay. So these are some of the locations from which the LCI methods have been developed. So now let us go to LCA interpretation. So the key features of interpretation phase, basically the systematic method to identify, qualify, control, evaluate, and present conclusions based on the results of the LCI and or LCI phases in order to fulfill the goal of the study. Okay, so that is the main feature of interpretation phase, to identify, qualify, control, evaluate, and present conclusions based on the results of the LCI and or LCI phases in order to fulfill the goal of the study. The iterative method, basically it is an iterative method basically which contains of three elements. One is identification of significant issues. Second is evaluation considering completeness, consistency, and sensitivity checks. And thirdly is conclusions, limitations, and recommendations. So firstly, identify significant issues. Second is evaluate, consider Evaluation considering completeness, consistency, and sensitivity checks. So we'll see the definitions of all these terms. And finally is conclusions, limitations, and recommendations. Okay? So this is the flow chart or the pictorial representation of the interpretation procedure. So the based on the other three important parts of life cycle, which is goal and scope, LCI inventory, and LCIA, that is impact assessment. So we basically have we firstly go for identification of significant issues. Okay, so we'll try to find out the significant issues which is the first element basically. Then if everything is all right, we go to evaluation. Okay, so evaluation is checking for completeness, consistency, and sensitivity checks basically. And there are some other checks also minor, so you can evaluate. So if it is not okay, okay, so if it is not okay, so you will again come back to identification and significant issues. Okay, so if they don't seem to be okay, we will again revert back here, and we'll also again find the significant issues. And if those issues are very serious, so we'll again go back to impact assessment and inventory. Okay, and so for interpreting whether everything is for interpreting the checks, okay, whether it is okay or not, we will refer to the GNS, that is goal and scope. Okay, so after interpreting and finding if everything is okay or not, if it is okay, so it is okay in complete. If the completeness check has passed, consistency check and sensitivity check has passed, okay, so then we can go for conclusion. Okay, so conclusion is basically we will try to find discuss the the output basically. We'll recommend what can be done. Okay, we'll discuss the recommendations, we'll find the limitations, and also report. Okay, report the changes required. Okay, so these are some of the goals. That is a third goal. If the first two checks have been completed, okay, so first two points have been completed, then we can go for conclusion, recommendation, limitation, and report. And that is the whole interpretation, and that can be used for some direct applications. Okay, so this has been taken from ISO 14044 2006. Okay, ISO is International Standardization Organization. Okay, so now let us see what is identification of significant issues. So structuring results of LCI and LCIA in order to identify significant issues according to GNS, that is goal and scope. So we have to that is significant issue identification is basically structuring the results of LCI and LCIA in order to identify the significant issues according to goal and scope. And it must account for the different methodological choices such as hypothesis, multifunctional processes, excluded processes, impact assessment method, etc. And the ISO standard ISO standard does not indicate what are the significant issues for a specific case. So these cases are basically general specific. Okay, so the ISO standard, it is basically giving a general cases for which we need to find out the specific significant issues. Okay, so it is not for a specific case. Okay, they do not indicate what are the significant issues for a specific case. It is for a general case. So that is basically the significant issue. Now the evaluation, that is checking for completeness, consistency, and sensitivity. So it is for establishing and increasing confidence in studies conclusions. And according to goal and scope, we have to take into consideration the intended application of the study. Okay, and there are three types of checks: completeness, consistency, and sensitivity. And additional, this is additional to the data quality assessment. Okay, so these are the some of the checks in addition to the data quality assessment for evaluation. And what are the meaning? Let us further find what is the definition of completeness, consistency, and sensitivity. So as per the evaluation checks, the completeness check basically it is to ensure that all relevant information and data needed were available and used. That is basically completeness check. What is consistency check? It is to determine whether the assumptions, methods, and data were consistent with the goal and scope and were applied consistently throughout the study. Okay, especially for comparative studies. So that in order to find it, okay, whether the assumptions, methods, and data were consistent with the goal and scope and were applied consistently throughout the study. Okay, especially for comparative studies, that is consistency check. And sensitivity check basically it is basically uncertainty analysis, that is to assess the reliability of the final results and conclusions by determining how they are affected by uncertainties in the data and the various methodological choices made. So it is sensitivity check is basically uncertainty analysis to assess the reliability of final results and conclusions in order to determine how they are affected by uncertainties in data and various methodological choices being made. Okay, so this is an example of completeness check. Okay, so here there are various unit processes such as material production, energy supply, transport, processing, packaging, use, end of life. So the cross signifies that data entry is available, and dash signifies a basically hyphen signifies a no data entry is present. Okay, so if you see here option A, every data is available, and the question is it complete? Okay, so if it is yes, then it is okay. If it is no, then we have to check inventory. If it is questionable, okay, then also we need to check inventory, or also compare it with option B. Okay, so in option B you will see that say data entry available for except for packaging, every data is available. So if it is yes, no issue. If it is no, we have to recalculate or compare with A. So if it is no, yeah, we have to recalculate or compare it with A. If it is not found, then also we'll compare it with A if no data is there. And if it is questionable, then also we'll compare it with A. Okay, so this is how action needs to be done based on the completeness check. Okay, as per ISO 14044. And the sources of uncertainty, basically they can be various types, such as natural variability of measured parameters, such as spatial, is it that is variable in space, temporal, variable in time, imprecision in measures during data collection, random error, systematic error, data gaps, unrepresentativeness of data, time, geographical and technical coverage, model uncertainties, simplifications, linear model. Like basically model uncertainty means we are simplifying the model. Say for example, for unlinear phenomenon we are considering a linear model, so it is not correct. Okay, so it is uncertain. Uncertainty is linked to choices such as functional unit, boundaries, allocation, LCI method, etc. Lack of scientific knowledge, calculation, and other errors. So all these factors come into being for finding the sources of uncertainty. Okay, so as per the ISO 14040 terminology, so life cycle inventory, basically it is the phase of LCA involving the compilation and quantification of inputs and outputs for a product throughout its life cycle. Okay, a life cycle impact assessment, or LCIA, it is the phase of LCA aimed at understanding and evaluating the magnitude and significance of the potential environmental impacts for a product system throughout the life cycle of the product. And interpretation is basically a phase of LCA in which the findings of either the LCI or LCIA or both are evaluated in relation to the defined goal and scope in order to reach conclusions and recommendations. So these are some standard terminologies as per ICA 140 about LCI, LCIA, and interpretation. Okay, so we check the completeness check like this, and we have found the uncertainty sources. So this is also an example of consistency check. Okay, so like the completeness check, okay, here also is a table where there is option A, option B, and there are checks on data source, data accuracy, data age, technology coverage, time related coverage, geographical coverage. And so option A, so literature, okay, okay, option B, primary, okay. So we compare A and B, it is consistent, so action is no action. If it is not consistent, okay, so we have to revisit B. If it is consistent, okay, not consistent, study target, okay, and if it is okay, then no action needed. So if it is consistent, no action needed. If it is study target is okay, no action needed. But if it is other than that, we have to revisit. Okay, revisit B, which is the issue, we have to address that. Okay, until the consistency check is completed. Okay, so like this, it has been given in the ISO 14044 2006 as an example. Okay, so with this we will end the fifth week lecture revision. Okay, revision discussion. So let us now further try to understand it better by solving some problems related to that. So first problem is, which of the below is an advantage of aggregated life cycle inventory database? Okay. A, possibility for contribution analysis. B, user friendly. C, possibility to adapt datasets. Or D, possibility to create datasets. So out of A, B, C, and D, which is the correct option? Okay. So we have to find the benefit of aggregated lifecycle inventory database. So that this is basically, so if you remember that here in aggregated case, apart from user friendliness, everything is a drawback. Okay, However, in the disaggregated case, apart from user friendliness, everything is benefit. Okay, so simply if you say, see here, possibility for contribution analysis. So this is, it is a drawback for aggregated. So possibility to adapt datasets, it's a drawback. Possibility to create datasets, uh, so adapt datasets, adapt dataset drawback. Possibility to create dataset also drawback. So what is advantage? User friendly. So user friendly is the advantage. So B, user friendly is the correct option. As you can see, B, user friendly, correct option. Second question, which of the following stage cannot be ignored for conducting a comparative life cycle assessment between two waste management technologies for the same product? A, manufacturing, B, product usage, C, end of life, D, resource acquisition, A, B, C, E, D. Out of this, which is the correct option? So if you remember, in this case, waste management technology life cycle assessment case, this concept is basically, if you remember, it was get to grave. Okay, get to grave concept. So where the first four, okay, that is resource acquisition, manufacturing, distribution, and use, all those were not important. Okay, because we considered them, because we are considering on waste management. So those are null. Okay, those are not required. So we consider them to be, we can ignore those. Okay, but what can be ignored is the last stage, which is the end of life. Okay, so that is why it is get to grave. So C, end of life is the correct option. So if you see here also, that this was the diagram. So LCA on municipal waste management, the stages before the end of life are the same and can be excluded. So this is a get to grave study. Okay, so C, end of life is the correct option. Third question, in a manufacturing company, it is proposed to change the conventional production process with an advanced 3D printing process. It is known that raw material requirement, product specification, and end of life management of the product remains the same. The system boundary that will evaluate the environmental impact of this change with better efficiency is dash. A, cradle to gate, B, cradle to grave, C, gate to gate, D, gate to grave. So out of ABCD, which is the correct option? So if you see here, if you remember, what were the five processes or stages? It was raw resource acquisition, manufacturing, third was distribution, fourth was use, and fifth was end of life. Okay, so the first was resource acquisition. Okay, so the raw material requirement, basically resource acquisition, raw material requirement, so it remains the same. Okay, of the product remains the same. So that's why that is, because it is same, it can be ignored. So therefore it is not your, this is not from cradle. Okay, cradle is, it is not from cradle, it will be from gate. Okay, so that means A and B will be incorrect. Okay, only C, out of C and D, one will be correct. And because end of life is also same. Okay, uh, because end of life of the printing, this one, printing process will be same. Okay, production, so end of life of the production process of both conventional and 3D printing is also the same. So that's why it is, the grave is also not, grave is also not necessary, that can be ignored. Okay, so cradle is also not necessary, grave is also not necessary. What is necessary is in between. Okay, so it will be between, because product specification is also there. So I think it will be from manufacturing to the use. Okay, so that is where we have to find the environmental impact. Okay, so the system boundary that will evaluate that is from from manufacturing to your use. Okay, so that is basically gate to gate, C. Okay, so C is the correct option. So hence, since this change does not include changes in resource acquisition and end of life, and the overall goal is to compare the alternatives in the production phase, the system boundary will be gate to gate for comparative LCA. Okay, so it is basically for production phase. Okay, so it is, therefore it will be from gate to gate. So as you can see, C, gate to gate is the correct option. Fourth question: if greenhouse gases emitted in a process elementary flow, which of the following will be its first order of effect? A, sea level rise, B, damage to human health and ecosystem, C, infrared radiative forcing, and D, or D, increase in global temperature. Out of ABCD, which is the correct option? So if you remember that slide, so the global warming environmental mechanism cause and effect chain. So GHG emission was the elementary flow, which was the cause. Okay, and the effects were as such. So first order effect was infrared radiative forcing, second order was increase in global temperature, Third order effect was sea level rise due to water expansion and glacier melting, and nth order effect was damage to human health and ecosystem. So we are being asked which is the first order effect. So it is nothing but infrared radiative forcing. So C, infrared radiative forcing is the correct option. So as you can see, C, infrared radiative forcing is the correct option. Fifth question, choose the correct option. A, consistency checks ensures that all relevant information and data needed were available and used. B, completeness check determines whether the assumptions, methods, and data were aligned with the goals and scopes. C, the ISO standard is referred to identify the significant issues while interpreting results for a specific case. D, the interpretation of results ultimately reports the conclusions, recommendations, and limitations of the study. A, B, C, D. So out of this, which is the correct option? So if you remember, if you see properly, so A and B, the lines have been swept basically. So consistency, in place of consistency, it is completeness. Okay, completeness checks ensures that all relevant information and data needed were available and used. Okay, not consistency. It was completeness. So A is incorrect. Similarly, it is consistency check determines whether the assumptions, methods, and data were aligned with the goals and scopes. Okay, not completeness. Okay, so it was consistency. It is consistency. So B is also incorrect. Okay, C, A and B are incorrect. So C, the ISO standard is referred to identify the significant issues while interpreting results for a specific case. No, ISO standard is referred to identify issues for generic case. Okay, so for a special like for a general case, not a specific case. So C is also incorrect. So D is the correct option. The interpretation of results ultimately reports the conclusion, recommendation, and limitation of the study. Okay? So D is the correct option. So as you can see here also, completeness check ensures that all relevant information and data needed were available and used. Consistency check determines whether the assumptions, methods, and data were aligned with the goals and scopes. The ISO standard does not indicate what are the significant issues for a specific case, and the interpretation of results ultimately reports the conclusions, recommendations, and limitations of the study. So, D is the correct option. So, as you can see, D, the interpretation of results ultimately reports the conclusions, recommendations, and limitations of the study is the correct option. Okay. Sixth question, why the LCI databases are developed and used during LCA? A, because it consists of all the primary data specifically collected for the study. B, because it avoids the usage of secondary data which are not specifically collected for the study. C, because redoing data collection all over again for key sectors, base materials, energy production for each LCA would be incredibly inefficient. Or D, because it is mandated by government agencies. So out of A, B, C, and D, which is the correct option? So it consists of all the primary data specifically collected for this. So this is not true. So it only consists of key data. Okay, the main primary data, because data like the in the for any process the elementary flows can be infinite. Okay, so it can't consist all the data. Okay, collected for required for a study. So it does not contain all the primary data. Okay, so this is incorrect. Second is, it avoids the usage of secondary data which are not specifically collected for the study. So that is also not true. Okay, so it does not avoid any usage of secondary data. So the secondary data is also provided in the database. Okay, so this is also incorrect. A and B both are incorrect. And C, because redoing data collection all over again for key sectors, base materials, energy production for each LCA would be incredibly inefficient. So this is correct. Okay, so doing like if you want to collect specific data for each even for key sectors, it would be incredibly inefficient. So you have to go with general data, not specific data. So that's why the LCA database is required. Sorry, LCI database is required. So that is correct. And D, because it is mandated by government agencies. So till now the government agencies have not mandated to use LCI database for performing LCA. It is up to the company how they perform. Okay, organization or company how they perform, it is up to them. So D is also not correct. So what is correct is C. Okay, because redoing data collection all over again for key sectors, base materials, energy production for each LCA would be incredibly inefficient. Okay, so LCA databases, if you remember this slide, LCA databases practically impossible to quantify all the flows of all processes. Okay, so it has been written. The length of supply chains is in theory infinite, because infinite elementary flows may happen. Each economic activity is linked to almost all the other. Okay, so even if only limited to the most important processes, redoing the data collection all over again for key sectors, base materials, energy production for each LCA would be incredibly inefficient. So therefore we suggest the use of LCI databases. Okay, so that is suggested because of that. So therefore C, because redoing data collection all over again for key sectors, base materials, energy production for each LCA would be incredibly inefficient, is the correct option. Seventh question, which of the following is one of the available life cycle impact assessment methods? A. Gabi, B. Simapro, C. Recipe, D. EcoInvent. So out of A, B, C, and D, which is the correct option? So Gabi is a basically software. Okay, so it incorporates the complete life cycle assessment software. It incorporates complete life cycle assessment uh, process stages and processes. So it includes everything. Okay, so it is not a basically life cycle impact assessment method. So it incorporates various other methods for life cycle impact assessment. So this is a software. So it is incorrect. Similarly, Simapur is also a software which incorporates inventory impact assessment and interpretation as well as goal and scope. So these are softwares, so it is not a impact assessment method. Okay, so this is wrong. So recipe, yeah, so recipe is a life cycle impact assessment method. Okay, so recipe, it is an example. Similarly, impact 2002 plus, that is also impact assessment method. So this is a correct one. And EcoInvent, this is basically a database. Okay, so this is an LCI database, it is not an impact assessment method. Okay? So out of this, C, recipe is the correct option. So if you can see here, so available process databases. So from government agencies and research centers, EcoInvent Switzerland. So it is a database, LCI database mainly. IVM LCI data Netherlands, Spine CPM Sweden, IDMAT Netherlands, ELCD Europe, US LCI United States, Industrial Association Plastics Europe, FEFCO Europe, and software developers. So if you see here, Gabi is software developer from Germany, made by IKPPE Europe. Simapro and EcoIDR made by company Pre-Consultants from Netherlands. Umberto is from IFU company Germany. Team is from Ecobilan France, and one more is from Athena Institute Canada. So these are the LCI methods: Eco Indicator, EDIP, EPS, CML, Impact 2002 plus, JPIX, Lime, Swiss Eco Scarcity, Tracy, Recipe. Okay, so recipe is the option, correct option. Okay, so if you see C, recipe is the correct option. Eighth question, which of the following is are not mandatory elements for life cycle impact assessment? So A, weighting, B, normalization, C, characterization, D, aggregation, A, B, C, D. So if you remember, characterization was important, but apart from that, normalization, weighting, aggregation, so these were not important. Okay. So if you remember this slide, so LCI procedure, mandatory elements are selection of impact categories, category indicators, and characterization models, assignment of LCI results, classification, calculation of category indicator results, that is characterization. So that results in category indicator results, LCI profile. Okay. So optional elements are normalization, weighting, and aggregation. So if you see normalization, weighting, and aggregation, A, B, and D. So not mandatory elements are A, B, and D: weighting, normalization, and aggregation. So as you can see, answers are correct answers are A, weighting, B, normalization, and D, aggregation. Ninth question: at the characterization stage, which parameters are used to calculate category indicators or impact scores? Okay. A, characterization factor of an elementary flow for a particular impact category. B, LCI profile related to the functional unit. C, elementary flow related to the functional unit, or D, LCI profile related to the reference system. So out of A, B, C, and D, which is the correct option? So if you see, if you remember this, so LCI practice, choice of LCI method, pre-established choice of impact categories, category indicators, characterization model factors. So for this is one, first is choice of LCI method, second is classification, third is characterization, calculation of category indicator results or impact scores. So this is the formula. Sj is summation of CFJI into Mi. Okay, so CFJI is characterization factor of elementary flow I for impact category J. So that is this one, A, characterization factor of an elementary flow for a particular impact category, and other is your this Mi, elementary flow related to functional unit, which is C, elementary flow related to the functional unit. So B, LCI profile related to the functional unit is not there, and D, LCI profile related to the reference system, that is also not there. So A and C are the correct options. So at the characterization stage, which parameters are used to calculate category indicators or impact scores? So we need A, characterization factor for of an elementary flow for a particular impact category, and C, elementary flow related to the functional unit. Okay, so A and C are the correct options. So as you see, characterization factor of an elementary flow for a particular impact category, and C, elementary flow related to the functional unit are the correct options. Last question, question 10. A sensitivity check is performed to assess the reliability of the final results and conclusions by determining how they are affected by uncertainties in the data and the various methodological choices made. Which of the following could be the sources of uncertainty? A, natural variability of measured parameters. B, lack of scientific knowledge. C, precision in measurements during data collection. D, simplification of predictive models. So out of A, B, C, and D, which are the sources of uncertainty? So if you a few slides back only we discussed that. So these were the sources of uncertainty. Okay. So one is nature. So if you see natural variability of measured parameters, so it is the first one. Okay. So this is correct. Okay. Second is lack of scientific knowledge. So this is also correct. So this is also reason for uncertainty. C is precision in measurements during data collection. So it is imprecision in measures during data collection. Okay, so not precision, it is imprecision. So this is a good thing. Okay, so this will lead to certainty. Okay, but we want sources of uncertainty, that is imprecision. So C is incorrect. Okay? And this simplification of predictive models. So this is this. Okay, model uncertainty simplification, linear model for unlinear phenomena. So that is also resulting in uncertainty. So A, B, and D. A, B, and D are the correct options. So as you can see, accepted answers are A, natural variability of measured parameters, B, lack of scientific knowledge, and D, okay, simplification of predictive models. Okay, so these are the correct options. So yeah, so with this we come to the end of today's discussion. So let us meet next Sunday with the 6 week lecture notes. Okay, so with this I would end today's discussion. Good night.